All right, I'd like to now talk about this mysterious force in the universe called dark energy. But in order to do that, I need to get back to the scale factor. What you're looking at here is the scale factor versus time, and the dashed green line is an empty universe. It's a theoretical line where the scale factor is proportional to the time. And you can see the red area there, that marks where we are now and how everything looks very flat in our universe. You wouldn't be able to tell the universe whether it's empty, except for, of course, the matter. But if you were just looking at the scale factor, or whether it was the yellow curve, or as we're going to see, the blue curve, or whatever, they all come together because we're setting AT now equal to 1. And you get then this yellow curve from a universe that's going to have mass in it, but continue to expand and slow down because of that mass, but not come back in on itself. Now in the next diagram, this is a closed universe. The previous one was the open universe. The closed universe comes back down on itself because there's enough mass in the universe, if you may remember, to actually collapse the universe and cause the big crunch. And as I mentioned to you before, it's very difficult to see which one of these universes we live in, because right now all of these all of these curves kind of come together, difficult to discriminate between them. And of course we can't look into the future, so we've got to look back in the past, and so it's clear that in order to determine the scale factor and how it looked in the past, we have to go back and measure something deep into space. If you don't measure it deep in space, then you're going to find that there's not much separation between these curves, so it's hard to find out what kind of universe you live in. Whereas the farther back in time you get, the more separation there is, as you can see, in the three curves, and so there's more chance that we'll be able to define what kind of universe we're in. Of course, the problem is trying to find something far away in space that we can see and then accurately measure its distance through its red shift. If you remember, the scale factor is equal to 1 over 1 plus z, z being the red shift here. So if we can get an idea of the redshift and therefore determine the distance, then we can see how the scale factor varies with time. And so that's what was happening in the late 1990s. Well, actually started in the mid-1990s. We started getting telescopes good enough to be able to see, or of high enough quality to be able to see great distances out into space. Oh, by the way, scientists by that time were realizing that the closed universe was going to be a hard sell, because if you look at it, it comes down, and it doesn't show this in the graph, but it comes down and it strikes the timeline at about 10 billion years. So we're finding galaxies in stars in our own galaxy that were older than 10 billion years. So we knew that there was a problem with the closed universe, and that probably we didn't live in a closed universe. The main thing I want to now talk about is type 1 supernovae, because it was discovered in the 1990s that we could measure the distances to these type 1a supernovae, and they also were extremely bright objects, so we could see them at great distances in the universe. The only problem was they were kind of rare, but it was a start. If we could measure enough of them, in various directions in the galaxy, then we could get some idea potentially of distances. But in order to explain to you how we can use type 1 supernovae to understand distances, I've got to go back to talk about stellar evolution and basically how stars evolve. So let me show you this diagram. It's a Hertzsprung-Russell Diagram, very famous in the world of astronomy. And the Hertzsprung-Russell Diagram graphs on the x-axis the color of the star, which is directly related to the temperature. As you can see there, the red stars fall around 3,000 degrees. You get stars the size of the sun, they're about 6,000 degrees. And you go on all the way on up towards where the y-axis hits the diagram. You're getting stars that have temperatures of 30,000 degrees Kelvin or greater even. Now on the y-axis we're plotting luminosity. You may remember that luminosity is essentially intrinsic brightness. I won't get into the differences in this course, but the luminosity gives us an idea of what the true brightness of those stars are. So we're negating the distances that they are away from each other so that we can compare them. And one of the first things that should strike you about the Hertzsprung-Russell diagram is that most of the stars that are burning hydrogen, well, not most, all of those stars that are simply burning hydrogen and turning it into helium through fusion fall on this so-called main sequence. The main sequence, again, is simply those stars that are burning hydrogen in their core, fusing hydrogen to helium, producing a lot of energy. And I have to emphasize now, and this is an important concept, I'm sure you're aware of it to some extent, but when a star starts to burn, the hydrogen being fused to helium, you know these are nuclear explosions going on, and there are lots of them. So you have this desire for the star to blow itself up. But working against that is this gravitational pull inward. And these two forces are working against each other so that there's a very fine equilibrium between the size of the star and the amount of fusion going on. For example, the bigger the star, the more gravitational pull. And by the way, the faster the hydrogen is eaten up. So from that, we know that the larger stars live shorter lengths of time than smaller stars. Let's take, for example, the sun, which you can see right here. The sun has a life expectancy of about 10 billion years. Now, we've already lived for about 5.5 billion years. We'll get into how we can determine that number. It's actually 4.567 billion years. We've lived that long, and we expect another 5.5 billion years or so before the sun burns itself out. But first I want to continue on this idea that the larger the star, the younger it is. You see the age of the sun is 10 billion years there. Then you go on up, the next one is 1 billion and up to 100 million and then 10 million. So these big stars that you see on the main sequence up there, they're only lasting for very short periods of time. I mean, 10 million years to an astronomer is a drop in the bucket. It's a very short period of time. Compare that to the 10 billion years that we anticipate the sun living before it burns itself out. I use the word living loosely here, but you get the idea. Now, a thing happens after the core of a star eats up its hydrogen fuel and converts it to helium. Well, I think you can realize that the gravitation takes over, and so the star starts to collapse on itself because there's less pushing out. And when that happens, well, you start to have more hydrogen being thrown into the core, and it's burning then, and it causes more fusion reaction of hydrogen to helium, and it also starts up helium reacting to form larger elements like carbon. And so you've got a lot of heat generated all of a sudden, and so the star, the outer parts of the star expand. And this is when we go to forming the red giants, where you can see in this area. If the star starts out big, then you're going to get the formation of a super red giant. We call them supergiants. Or you can get just regular red giants, and that would be what the star would form. Now, because the star is young, not young, but because the star, the size of the sun is rather small, when it forms a red giant, it's only going to convert most of its helium into carbon. You're kind of left over with carbon. And towards the end of its life, that carbon is going to be, not the carbon, but the outer parts of the star, which have puffed up, are going to be sloughed off and sent into space, and you're going to be left over with a white dwarf. And let me talk about the differences between white dwarfs on this diagram. The reason that red giants fall above the main sequence is because they've puffed out, so there's more area, there's a higher luminosity because of the increased surface area, but also because it's expanded, it's cooled itself down. So you're going to see them falling to the right of the main sequence here on this diagram. Whereas with white dwarfs, you've concentrated the part that doesn't get sloughed off is that area that's converting helium to carbon and sometimes carbon to oxygen and all the way up to iron if you get a star big enough. So you form white dwarfs, and white dwarfs are small and concentrated, so they're hotter certainly than red giants. So they move to the left, but because they're smaller, their luminosity is lower. I hope that's clear. So we have then these two regions on the Hertzsprung-Russell diagram that very clearly shows how the evolution of stars take place and why they move to different areas in the diagram. And stars between a mass of about 0.3 and 8 solar masses, they're going to go through the red giant phase. Those that are lower than 0.3 we don't have to worry about. They go directly to white dwarfs. Those that are bigger than about 8 solar masses, well, they're going to go into the supernovae, which we're going to talk about. Those are the type 2 supernovae. I'll get back to those a little bit later on. Right now we want to focus on type 1 supernovae. In the case of a type 1 supernova, the process goes through everything that we're seeing here. The only difference is that we have two stars, a binary star system. Now, maybe you don't know this, but we have a lot of stars in our universe that are binary. They exist with another star. And so when they go through the supernova phase, when one of those stars goes to the supernova phase, nothing really happens. It goes to the supernova phase, doesn't affect the other star, becomes a white dwarf. Now remember, we've got a white dwarf, which is a very concentrated amount of mass. It sits next to a regular star. And then when that star goes through its red giant phase, that white dwarf, when the red giant starts to expand, that white dwarf's gravitational pull starts to suck in some of the mass from the red giant. And while then things go crazy because you've got extra hydrogen coming onto the white dwarf, and this then causes further reactions, and sure enough you get an explosion and you form a supernovae. And in this case you're looking at a supernovae type 1a supernova next to the NGC 4526 galaxy. And just an example here to show you, and this little diagram shows you what happens when you get a type 1 supernovae affected. It lasts for about a month and a half where it's very bright. In fact, I think I read somewhere where the amount of energy is equal to all of the energy generated in our galaxy when a supernova explodes. So an immense amount of energy in one isolated locality, and that's why they're so easy to see across the universe for great distances. Now, that's the key though. How do we use this known output of energy based on this curve? It peaks there and it's got nickel drawn next to the peak. That's because during the supernova, when it's exploded, the gases are still fusing, and you get helium fusing all the way up to nickel, which is really what's causing most of the energy peak, is the elements, most of the elements fusing to nickel and the production of nickel, which by the way decays back to iron, which we'll learn more about a little later on. And that peak, the nickel peak there, occurs after 22 days in the cycle of a supernova 1A. And the important thing here is cycle, because what we can do now is we can know where the supernova is on this curve when we're looking at it. And we can take then, and we know precisely the energy, and therefore we know what the true brightness should be. and we can compare it to the apparent brightness, and that'll give us an estimate of the distance to the star. Now, it's more complicated than that, but that's basically the concept. In other words, we can use type 1 supernovae to determine how far away they are, and as a consequence, get an idea of the scale factor of the universe. And that's pretty exciting. And we weren't able to do that until the 1990s, when the instrumentation became good enough for us to be able to determine that. Well, two teams were working on this in the 1990s, and they started getting data, and they started plotting their data on the scale factor versus time graph, as you can see here. And something astonishing happened. As you can see from the curve, the red curve, the type 1 supernovae not only didn't fall on the blue line, that is the closed universe, or the green line, which is the open universe that expands forever, but it was falling even to the upper part of the line where we shouldn't have any mass in the universe. Now, obviously, this doesn't mean there's no mass in the universe. But what does it mean? Well, I heard a talk by Brian Schmidt, who was one of the co-discoverers. He headed up the Australian team that discovered the scale factor and what it did back in time using type 1 supernovae, type 1a supernovae. And I heard him say that when they first got this data, that they thought they'd made some mistakes somewhere, that they really didn't believe it was correct because it was so bizarre. And then they started looking at their data, they verified it, and then they heard that the other team was getting the same results, and so they were more confident, and they went ahead and they published it. And astonishingly, now, what does this tell us? Well, if you look at the blue and the green curves, we would expect them to curve back because we have mass in the universe, and the universe would gradually slow down. But if you follow the red line out, it's going to increase upward. It's going to increase away from coming back. So in other words, what this tells us is that not only is the universe infinite, and it will continue to expand, I should say, forever, but it will increase in its expansion. That is, the universe is accelerating. Well, I hope I don't have to tell you that this is probably one of the great discoveries in all of science, that we live in a universe that is not only expanding, but it's accelerating as it expands. Now here's where it gets kind of spooky. Let's talk about what's causing this, because it appears that we've got some sort of energy being generated. It's almost the kind of the opposite of what gravity's doing. Gravity's sucking everything into it, but this is pushing everything outward. So it's like creating an outward force, or to push the universe, if you will, out into into this accelerating expansion. It turns out that Einstein actually thought about this back when he was thinking about general relativity, and he came up with something called the cosmological constant, which would make the universe accelerate. And the way he conceived of it was that as the universe was expanding, it was actually creating energy. And this then forced the universe to expand even faster. And the key here is that this energy permeates space, and that you're creating new energy as the universe expands, which then creates more and more expansion, which then creates more energy, and you get the idea. And so we have something out there, and if anybody tells you that they know what it is, they're lying to you. It doesn't work that way. This energy is, wow, I don't know what to say. It's called dark energy for a reason, and that's because nobody knows what it is. So we have this mysterious energy that permeates space. It seems to be created as space expands more and more because our space is accelerating, and we refer to it as dark energy. Lots more work to be done on this, but isn't it great that we live in a universe where we can understand these things? You know, I can't help but pointing out that if we were born, well, not us, but if we saw intelligent life evolve billions of years from now, well, they might be living in a universe where it's expanded so far that you couldn't see any other galaxies out there, and so they wouldn't be able to figure out what we know today, which is that we're living in a universe that is expanding. You got this graph down here that tells you now what the universe, and guess what? We know what the universe is made out of. Now, you may say we don't know, but we do know. We do know that it's made of some mysterious energy called dark energy, and it makes up 74% of the universe. And that is forcing the universe to accelerate as it expands. And we also have 22% dark matter. We've talked about dark matter. Well, dark matter's out there. Thank God it's out there because it helped bring galaxies together. We talked about that, quantum mechanics, quantum fluctuations, I mean. And then finally, and almost astonishingly, only 4% of our universe is made up of material we can see. That's the intergalactic gases and, of course, things like stars and supernovae. Well, I want to show you these two gentlemen. One of them is Brian Schmidt. He worked with a group out of Australia. He's an American from Harvard. And Saul Perlmutter, and he headed up a team. Both of them discovered type 1A supernovae, that is not discovered, but used type 1 supernovae to determine distances and then scale factor, and discovered that the universe was accelerating, and they won the Nobel Prize in 2011. So that should give you just how, or I should say, should give you an idea of just how important this discovery was.